So as a part of your second lab, you'll be designing adders of different styles. So you'll start with a full adder, that is 1-bit full adder, then go with a ripple carry adder, then use that to build different other adders like carry select adders and other stuff. The design part should be pretty straightforward from the classes and regular digital design, but the important things that I'll be covering in this video is going through the rest of the parts, like finding the reports in your folders and how to read them, and what stuff is present in those reports and things like that. So as an example, I have used a ripple carry adder. I mean, I have the entire lab 2 done on my side, but I'll just be showing the ripple carry adder, that is full adder of 1-bit and ripple carry adder of 4-bit. I have a test bench for it, but I'll not go through the simulation because you are familiar with it from the first labs videos. So this is my full adder. If you can see, there are two XOR gates, two AND gates, and one OR gate. It takes inputs of A, B, and carry in. It gives out sum and carry out, and this takes in 1-bit values. So it should be pretty straightforward if you look at the structure of this. And then I have used a new module called RCA, that stands for Ripple Carry Adder, which has 4 bits of input of A and B, and then a carry in. It has a carry out, which is 1 bit again, and an output sum of 4 bits. And then I have a wire which is of 3 bits width, called carry, that I have used for internal connections. So if you remember Ripple Carry Adder from your lectures, it should basically be 4 full adders, wherein one carry out from the first module goes to the second module, and so on. So the same thing happens here. There are 4 full adders with inputs going into each one of these modules. Like 1 bit of input goes into one module, and you get the sum output. The only place they are connected is near carry, where carry of F0, that is carry 0, goes in as carry in of F1, and so on. And your final carry out is C out. So if that part is clear, I have a test bench for it, which runs through all the possible cases from 10-bit value, from a 9-bit value of 000 to all ones. And then at each point in time, it will exhaustively test all the possible conditions for that particular RCA. And I will just do, because my top level module is RCA in this case, I will do analysis and synthesis, and then I'll show you what to find in the output files. That should be the only different part of this lab. Rest of the things should more or less be same. So if I just double click this, yes, I want to run analysis and synthesis again, because for video. But if we run it, you should basically find a few warnings, probably no errors, hopefully no errors. And once that is done, you can open the same directory in which you have done your project, or you have initialized your project. And now you should see a directory called output_files, and that is something we are interested in. If you remember lab 1, we have skipped the part where we were using timing or including the SDF files, but it is pretty straightforward. You can include SDF files wherever you want in this edition, and if you include those, you will get the .sta outputs, that is static timing analysis outputs. But I don't think that is required to actually find the delay of your circuit. If you find the number of gates and interpret the delay in terms of number of gates, that should be enough. So now that our analysis and synthesis is successful, if we look at our project location, we have this called output files, and we have a .done file, 2 report files, and a summary file. So I have opened this in Notepad++. It should basically work in WordPad, Notepad, or Notepad++. Anything works. So if we go through to the done file, it should basically give the time at which you are done with it. And then after that, if you go to the flow.rpt file, that should basically give the flow in which the tool has worked. So it should basically say your flow summary. your flow status was successful and the top level entity was RCA for this device and the timing models were final. It gives the total number of logic elements found and the actual flow that it took. So you can see that it started with the EDA data output format and then went into max scores and things like that. So because you performed analysis and synthesis alone, it should basically show only that in your flow. But if you remember, there are a bunch of other things that happen once you do the pin assignments, and all of those will be showed here if you open the report after your pin assignments and things like that. That should basically be your flow report. Your RCA map is something interesting, something important to look at. Uh, this this is a map of RCA, that is my ripple carry adder. By map, it means the way in which your elements inside are arranged. So again, my top level entity is RCA. You will have a summary of all the analysis and synthesis that is done, like the number of carry buffers used or the RAM, if at all it is used, number of state elements used, and different things. It's a fun activity to go through these reports, and if you if you plan on staying in this field, this is how people deal with things rather than actually dealing with GUIs. So go through all of these and see what is interesting for you, and then it shows how much time it took and what the parallel compilation and other things were, and then it shows you what all files were used in this particular compilation. For us, it was just full adder and ripple carry adder, and the total number of logical elements in our design was 4, and what were different modes used according to the your user manual and things will be discussed here. And the number of IO pins are basically input output pins. We had four four input sorry 4-bit input, 4-bit output. So those count for 8 gates, carry in, carry out. Those are two more. That is 10 IO pins, and then 4 more for some output. So this pretty much shows what we have done, and then it shows how your full adder was arranged and what were the logic combinational units used inside it and how many logical blocks were used inside it and things like that. It's a pretty fun report to go through, and this should basically answer the questions of your first part, or majority of the part of it. If you look at the summary now, the summary shows a summary of all the reports you have seen so far. So we did not use any registers in here because you did not use any always statements, because you were not asked to use some. You did not, and it shows total number of pins and total number of logical elements. To have a much cleaner picture about all this, it is better to do open these reports after you assign pins and perform compile design completely, and then you'll have better kind of reports that are more reliable than what you saw just now. So these reports kind of give you a rough idea as to how your design will fit or what is the size of your design on your board. So go through those reports, see where the area numbers are, see where the delay numbers are, and try to analyze how things work. And the same thing should apply for the other adder modules as well. I'm not going through the design part in this particular video because that is most probably covered in class, or it is pretty straightforward from your lab handout, but I'll be helping you out in lab anyway, so that should be fine. So let me know if you guys have any other questions, and that's it for this video.